So if we want our models to be trustworthy and effective and useful for developing resilient infrastructure models, then there are several kind of important things that we need to be able to do. We need to be able to avoid spurious precision, identify key sources of uncertainty so that we can understand sort of when our models stop becoming valid and understand how to improve models as well. And we also need to be able to identify robust designs. So we need to be able to sort of look at which designs perform well enough across a whole range of possible futures. And I suppose I'm here to argue that uncertainty quantification and sensitivity analysis provide a really good methodology for addressing these challenges. So just a sort of quick intro, what I mean when I say sensitivity analysis is this kind of two-step process. So what we first of all do is we propagate a kind of range of uncertainties through the model via Monte Carlo simulations. So we sort of identify the inputs which we consider to have significant uncertainty and define the kind of bounds within which this sits, and then we send this through the model. And then in the second step, we analyse the input-output data set. So we're looking at how these uncertain inputs translate into outputs. And the methodology that we kind of use in our project and that we're hoping to implement into the DAFNI platform allows you to quantify this uncertainty, quantify the sensitivity, and also do a kind of element of stress testing. So yeah, our project, which we call USARIS, is going to hopefully set the foundations for including this methodology into the DAFNI platform so that we can demonstrate the value of these methods to the whole DAFNI users community. So the integration of this into DAFNI is going to be conducted via two, or well actually maybe more than two now, pilot applications or DAFNI workflows. And these are going to be focused in kind of two sectors. So we're going to have a couple of workflows which work with water models and also a couple of workflows which work with energy models. And what we're going to do is we're going to integrate some sort of pre-existing packages from the SAFE toolbox into DAFNI and apply the sensitivity analysis using this. And the idea is that these workflows will be useful for training and dissemination throughout the project and be like a really good platform for us to kind of share our methodology. So what have we done so far in the project? The main output of our project is these kind of pilot applications. We've got one of these already ready to go, which is working with a hydrological model. And this is on DAFNI as a workflow. We're also sort of in the process of getting on with a local analysis. We're locally doing the sensitivity analysis for a wind power model. And we're also working with Anna on her project to apply sensitivity analysis to PyWare as well. And as part of the project, we've got like a GitHub repository going and we're trying to have everything kind of open and out there for people to take a look. So I thought I'd just quickly talk through the steps within which we actually run a sensitivity analysis on DAFNI. So I guess it's a slightly different methodology to how you do it locally, just to work with the platform. So the first step is to upload the model and the data to DAFNI. We've done this, as I say, for a hydrological model, and all of the parameters that we consider to contain uncertainty are kind of in DAFNI as input parameters, so you can see them on the screen here. We then need to make a workflow to run this model on DAFNI. That's pretty straightforward. We then use the nice and convenient looping function to loop over this workflow and essentially iterate through these input parameters, and that we define ranges for that as well. And then very usefully, DAFNI has this facility for us to visualize the outputs. This is done in a Jupyter notebook, and this is where we kind of really do the sensitivity analysis and we quantify the uncertainty in each of the inputs. So I'm not going to go into this in too much detail because we spoke about this application in our DAFNI seminar. So if anyone wants to hear about this, then you can go and watch that. But we have already developed one of the pilot applications, which is this hydrological model, where we apply the sensitivity analysis in a really simple way. This is a very simple application, but it shows the kind of pros and cons of what we're trying to do. And then this is the application that I've been working on mostly over the summer. So what we're doing is we're applying a sensitivity analysis to a wind power model. So what this model does is it transforms wind speed into wind power. It's traditionally used for things like wind farm resource assessments. So it might be that we know we want to build a wind farm and we have a potential site, but we just want to check that the sort of year-to-year variability in the wind power is sufficient. We want to make sure that enough power will be generated. So it seems as though the main input to this kind of model is the wind speed time series, but actually there are a number of other uncertain decisions that we have to make along the way. And what we're doing here is we're conducting a sensitivity analysis where we're considering all of these other uncertain decisions against the influence of the year-to-year variability. And what we hope sort of happens, I suppose, is that the year-to-year variability is what's controlling the model output, because that's really why we're using this model, but the sensitivity analysis will allow us to kind of confirm this. So as well as varying the year, we have 83 input years for this sensitivity analysis. We also varied the height at which we took the wind speed data from the reanalysis. We also varied the time step, and this wind power model takes a power curve as well. And this is a sort of user decision, the power curve, which is selected. So we put 19 power curves into the sensitivity analysis to also look at the influence of that choice. And also we varied one of the parameters of the model, alpha, within sort of realistic bounds to look at how, again, that choice is going to influence the model output. And the output that we care about in this instance is the mean wind power, which is generated in the chosen year. So the results of the sensitivity analysis are on the screen now. If you take a look at the box plots, what we can see is that actually the power curve has the highest sensitivity index. So on the y-axis of the box plots, you're seeing the sensitivity index. What this means is that the model outputs are most sensitive to this choice. And since these kind of wind power models are really usually used to investigate the year-to-year variability, the fact that the power curve is having such a large influence is kind of a very useful thing to know. And if we want to reduce the uncertainty in the outputs of this model, then this is telling us that we really need to make sure we've selected the right power curve, or the variability that we see in the different years is going to be potentially masked by this, and the results are potentially not very reliable. There's also some scatter plots on this screen here, so as part of the sensitivity analysis, you can kind of look at the visual relationships between when we vary the inputs and what that does for the outputs. So in the case of the power curve, which is the purple dots, we can essentially see that as the shape of the power curve changes, we get a kind of higher mean wind power output. So it just shows the control that the power curve is having on the output. And similarly, if you look in the blue, we can see that the mean wind speed from the chosen year is, as you would expect, having an impact on the mean wind power as well. So in terms of what our project has done for kind of community engagement, we've presented this work at several conferences. I was in Newcastle last week at the Climate Impacts Conference, and Hannah presented a nice poster for us at Risk and Resilience Day earlier in the year. As I said, we've done a DAFNI seminar as well, which is on YouTube, and we're planning some kind of workshops with stakeholders, hopefully with the Environment Agency and others, to kind of spread the word about what we're doing and encourage people to interact with our workflows. So just to also briefly touch on some of the challenges and the benefits and the impacts of our work, I think we found so far that the key challenge has been the kind of computational complexity of carrying out a sensitivity analysis. So it was nice to hear earlier that the looping functionality the cap is being increased, which is really great for what we're doing. At the moment, the cap is set at 50, which does allow us to do a sensitivity analysis, but it doesn't allow us to have as much confidence in the results. 50 iterations is not that many in this kind of context. So that was one of the key challenges, but I think actually we're making good progress on that. And then I guess the main benefits and impacts of our work are to do with these workflows. We hope that they're going to be a really easy way of sharing our methods and visualizing the results. And they already seem to be kind of facilitating collaboration. So we're also about to start working, like I said, with the PyWare project, and that's been made much easier by the fact that we have these workflows. So yeah, we hope that our methods are easy and transferable, and that our findings are going to help to promote more resilient infrastructure designs and best modelling practices as well. Yeah, I'll stop there. Thank you.